Okay, cool. Should be recording now. So the first thing, again, we're going to look at tree traversal. So there's various different ways that we can traverse through a tree. Each one of these can be used for different applications. So the first thing will just be like a mechanical question of like how to do these traversals. Next, we'll spend a little bit of time looking at kind of like different types of trees. So this question deals with BSTs, which is overloaded. In this case, means a binary search tree. Effectively, what that's saying is there's a tree where items to the left of a node will be less than whatever the value of the current node is. Items to the right should have values that are greater than. That property gives us a lot of like abilities to look up nodes in faster time typically. This question here is like how to verify if a tree actually abides by the properties here. The next question deals with game trees. So game trees are, I would say, both a really cool topic and also a very important topic. So for project 2, you'll be asked to build a AI to play this game, and the AI will be using a binary search, or sorry, not a binary search tree, a game tree. So game trees are not the most prevalent solutions to like AI problems. So if you hear like Google's doing cool stuff with AI, they're probably not using game trees. This is probably like a slightly older method, but it is something that's like a little bit more tangible, and hopefully like you'll appreciate like what you can do with it. The last question, if we have time, is just another question to give us some exposure to binary search trees. So we're going to be looking at these two different, so basically there's 4 different kinds of traversals that we're looking at. So DFS pre-order, DFS in order, DFS post-order, and BFS. So those are kind of separated into 2 categories. You can see that there are the 3 ones which are DFS, and then there's the one other one which is BFS. So DFS stands for, so DFS equals depth first search, and then on the other hand, we have BST, which is breadth first. So these are basically like 2 different kinds of ways of traversing through the tree. And then we can see in DFS, there's like 3 kind of variants of these. Those all are kind of just like different orders in which we might process nodes. But for the most part, like the actual traversals themselves are very much the same. So let's first take a look at what like a DFS traversal looks like. Then we can take a look at what each one of those different orderings for a DFS traversal looks like. And then we can look finally at what breadth first search looks like. So back way back in the day when I was in 61B, which feels like eons ago, let me see, where's the best place to do this? I'm gonna do it here and then I'll move it. So when I was in CSM for 61B, my mentor showed me 2 different things. So it was, and these are like very like coarse ways of thinking about DFS or BFS, but depth first search in its name is like depth. So what exactly does that mean? It's like you're trying to go as deep into this tree as you possibly can again and again. So if you imagine this tree is represented by like some kind of triangle like this, what we're trying to do is go to the bottom of the triangle repeatedly. So you can kind of imagine you're kind of filling in this triangle like this. You're kind of like going all the way to the bottom and sweeping through the triangle. On the other hand, a breadth first search is you're looking at levels of the triangle and you're kind of filling in from top to bottom. So these are, again, like 2 very abstract ways of looking at it. Depth first search tries to go all the way to the bottom of the tree and then sweep through it from typically left to right, although it often doesn't always matter. And then on the other hand, breadth first search is kind of like, I'm going to start at the top of the tree and go level by level through the tree like that. Okay, I'm going to go ahead and continue. So I'm just going to move these out of the way, put them up here, sure. So now let's look at what that looks like, a depth first traversal looks like in this particular tree. So what we want to do is we want to start at the very top node. So we're going to start at the top node here. And as we go here, again, we're trying to go as deep as possible. So it says that we should be processing the children from left to right. So in that case, we're going to go to the left first. So we started at 10. Now we're going to go to the left of 10. What's the left of 10? Okay, now it's 3. From this node, we're going to try and go, again, deeper in this tree, choosing the left child first. So now we're going to go to 1. So it's like we're going down the tree, then down the tree. Finally, we get to 1. So where can we go from 1? In this case, there's nowhere for us to go from 1. So what do we have to do? We have to go back up to the tree to the last node that we came to. So this is like the first hop here, second hop here. We then go back up to 3. Once we go back up to 3, then it's like, okay, are there still children for me to visit? In this case, there's a 7. So now you go down. This is going to get kind of messy. You go down to 7, and then again, you hit 7. There's nothing to be seen at 7. Now you go ahead and return back up to 3. Is there anything left to be visited from 3? No, there's nothing to be left from visited from 3. So then we go back up to 10. Is there still stuff left to be visited from 10? Yes, there is. So we go down to 12. Now that we go down to 12, are there any left children to visit? No, but there are right children to visit. So we continue to go down. Again, 13, there's no left children to visit, but there is a right child. We continue to go further down. Finally, we hit 15. Is there anything left to visit here? No, nothing left to visit here. So we bounce back up to 13, then we bounce back up to 12. At each of these levels, there's nothing left to be visited from here. So we finally get up to 10. Is there anything left to be visited? No. So this is kind of like, this diagram here is like fairly complicated, but the basic idea, let me change the color. The basic idea here is that we're starting at the top here. We're going down the tree. We're going here, seeing that there's still stuff to go. We're going down further. We finally get to 1. Now that we get to 1, we say, okay, there's nowhere for us to go, but we're going to try and continue to sweep from left to right. So we go back up and see that there's still something left to go here. So again, we go deeper. We go to 7. Once we're at 7, we say there's nowhere for us to go. We go back up to 10. We're going to continue sweeping by seeking like as far down into the tree as possible. So we end up going down to 12, all the way down here. And then eventually like we kind of return from each one of those. So that's like a very high level picture of what a depth first traversal looks like. So in this case, we have 3 different types of depth first traversals. So we have DFS pre-order, DFS post order. I'm going to change the order here because I think it makes slightly more sense than DFS in order. And then finally, we'll get to DFS. So these are our 3 things that we're going to look at here. So pre-order basically means the first time that you see something in the traversal, add it to the pre-order. Post-order means the best way to think about it is once we return from it, once we run out of children to go from here, then add that to the order. And then in order is a little bit different. So let's first look at pre-order. So pre-order is basically the first time you see this node in your traversal, add it into the pre-order. So this is, I'm going to go ahead and erase these arrows. I hope that's fine. We're going to go through this process again. I'm just going to use the laser pointer, and we'll just add things to this order as we go. So we start at 10. Now that we start at 10, what does that mean? That means that we've seen 10, so we should add 10 to our pre-order. From here, the next thing to do, we're going to continue along the same exact path. When we continue along the same path, the next thing that we do is we go down to the left, and we go down to the left. Now we're at 3. When we're at 3, what should we do? We see the 3, so we should add it to our pre-order. From here, again, we go down to the left. When we go down to the left, we see the 1. Once we see the 1, we should add it to our DFS pre-order. So in this case, we've made it all the way down, so we see 10, 3, 1. We said after we see the 1, is there anywhere else for us to go from here? No, there's not, so we return to the 3. Now that we're at the 3, is there anywhere else for us to go from here? Yes, there is. Now let's go down to the 7. Now that I've seen the 7, we should add the 7 to our pre-order. Okay, from here, we'll go, so we've hit the 7. There's nowhere for us to go from the 7. We return to the 3. There's nowhere for us to go from the 3. We now return to the 10. We've already seen the 10, so there's no need to add it here. We're going to continue down to the right because there's still children to visit here. We see that there's a 12. We add the 12 to our pre-order. There's still places for us to go down from here. So we go down to the 13. Now we'll add the 13 to our pre-order. And last but not least, we'll go down and we'll hit 15. When we hit 15, we'll add that to our pre-order. Finally, we'll have this sequence of returns back, but we won't add anything because we've already seen everything. Now we'll look at post order. So post order, I think, is a little bit more abstract or weird to think about. But again, we're following the same exact pattern of how we move through the tree. So what we'll do is, as soon as we see a node that has no more children left to go to, then that's when we're going to add it to the DFS post order. So basically, in this case, we're going to start at the 10. Are there still children of 10? Yes. So we're not going to add 10 to our post order, and we're going to continue moving along. We get down to the 3. We see, okay, again, there are stuff that we can do from here, so we shouldn't add 3 to our post order. We'll continue going. We get down to 1. When we get down to 1, is there anywhere for us to go from here? In this case, no, there's not. So now we're going to add our first thing to the post order. So basically, we're adding it to our post order because at this point, there's nowhere for us to go from 1. Okay. Continuing on, we'll go from the 1 back up to the 3. When we go back up to the 3, now we see, is there still stuff for us to go from here? Yes, there is. So we'll go down to the 7. In this case, again, we see there's nowhere for us to go from the 7. So there's no children / we visited all of the children here. So now we add 7 to our post order. We continue on. Now we go from 7 back up to 3. Is there anywhere for us to go from 3? In this case, there no longer is a place for us to go from 3 because we visited both of its children. So now we add that to our post order. Continue on, we go back up to 10. Is there somewhere for us to go from 10? Yes, so we don't add it to our post order. We go down to 12. Is there somewhere for us to go? Yes, so we don't add it. Is there somewhere for us to go from 13? Yes, so we don't add it. Is there somewhere for us to go from 15? No, 15's at the bottom. We visited all of its children / they don't exist. So we add 15 into the post order. We continue this walk back up. Is there anywhere for us to go from 13? No, we visited its only children or only child, so we add 13. Similarly, we add 12. And last but not least, we finally make it back up to the top node here. We visited all of the children, so now we add 10 to the post order list. So that's pre-order and post order. Like a very, very quick sanity check. In pre-order, you should always see the root node first. So that should always be the first thing. In post-order, you should always process the root node last because you have to see everything else, all of its children. So in pre-order, the root node should be first. And in post-order, the root node should be last. It's not like a surefire guarantee of like being able to be like, okay, like this is correct or not. But if you do a post-order and you don't see it as the last one, you do a pre-order, you don't see it as the first one, then you should know, okay, like something's up. The last one is DFS in order. So DFS in order is effectively, where should I write it? So DFS in order, that was a combo. So basically first you visit the left, then me, then right. So what exactly does that mean? The order in which you add things is you should first, this is a little, move that. So basically, you should first look at your left. So don't add yourself until you've visited all of your left. Then do yourself, and then do all the right. So in this case, that means that we should process, so if we're looking at 10, we should process everything to the left of 10. So we should process 1, 3, and 7 before we process 10. And then finally, we should process everything to the right. So basically, first do everything to the left, then do myself, then do everything to the right. So what exactly does that look like? Again, we're going to do the same exact traversal. We're going to start off at 10. Is there stuff to the left that still needs to be processed? Yes, so we're not going to add it. We're going to move to the 3. Is there still stuff to the left that needs to be processed? Yes. We're going to move to the left. Is there still stuff to the left to be processed? No, there's not. So now I'm going to add 1. 1 is the first thing that gets added. Next, we're going to say, is there anything to my right? There's nothing to my right, so I don't have to worry about that. I move back up to 3. I've processed all of my left, so now I'm going to add myself, which should be 3. Then, is there anything to the right? Yes, there's something to the right. Now let me go ahead and process that. In this case, similar to 1, there's nothing there, so we go ahead and just process the 7. Finally, or next, we're going to return to 10. Everything to the left has been processed, so we'll go ahead and add 10. We'll move on here. Is there anything to the left that needs to be processed? No, there's nothing here. So we process 12. After we process 12, we then move to the right. Is there anything to the left that needs to be processed? No. So we go ahead and process 13. We add 13. We next, again, move to the right. Is there anything left to be processed here? No, the only thing left is 15. So I go ahead and add them. The reason that this is called in order is if you're doing this traversal on a binary search tree, which again, in a binary search tree, at the root, that kind of splits the values by whatever the root node is. So in this tree, we can see that the root node is 10, which means that everything to the right, so all of these nodes, these are less than 10. All of these nodes, these are greater than 10. If that property holds throughout the entire tree, that means that you have a binary search tree. If you have a binary search tree, when you run an in-order traversal, you should get back all of the values in ascending order. So in this case, we can see the values are 1, 3, 7, 10, 12, 13, 15, which is exactly all of the values contained in the tree in ascending order. So that basically concludes all of the DFS examples. So then we'll move on to what BFS looks like. So I'm going to go ahead and just erase this. So the last one is BFS. So there's various different ways of thinking about BFS. The easiest way, or the most straightforward way, I think, to look at it is basically you're reading off this tree as if it was a book from top to bottom, from left to right across each row. So it's basically like, I'm gonna first look at the top row, that's like line 0. I'm gonna read that from left to right. I'm next gonna look at the next line. I'm gonna read that from left to right. Then I'm gonna look at the next line, read that from left to right, then look at this line and read that left to right. And you basically will just add them into the order in that order. So in this case, we start off on the first row. So the first row is 10. So we go ahead and add 10. The next row, it has 3 and 12. Again, we do it left to right. So we add 3, then we add 12. The next row has 1, 7, and 13. We'll again read them left to right. So we'll add them in this order: 1, then 7, then 13. And finally, we add in the very last row, which is 15. Okay, so that's basically what a BFS looks like. So instead of going from kind of like this, like it's going down the tree as deep as it can, it's looking at each of the rows of the tree and kind of going through the entire level of that tree. So you can also think of this as like some kind of level order traversal that processes all the levels of the tree in order. Cool. So I'm going to talk about two other things kind of quickly that are, I think, also important. So one is kind of, it's really just one thing, but how do you actually go about implementing these? So we're not going to talk too much about them. I believe there's code in the lecture slides about how you would actually implement them, but it turns out they can be implemented very much the same way, as long as they're backed by different data structures. So typically BFS is implemented using a queue. A queue is a data structure that is last in, first out, or LIFO, which basically means when you're adding values into it, it's just like a line. If you got into a line, the first person that got into the line, they'll be processed first. The last person that got into the line will be processed last. So if you use if you use BFS, you can associate that should be a queue. If you're using DFS, you should use a stack to implement it. So a stack is, so a queue is LIFO, again, last in, first out, and a stack is FIFO, which is first in, first out. So whoever got there last will actually be the first person to be processed. So if you're implementing DFS, you should use a stack, which is a FIFO data structure. If you're using BFS, you should implement that using a queue, which is the LIFO data structure. The other way that you can implement a depth first search is to use recursion. So recursion works. Why? Because recursion uses a call stack, and a call stack is just like a regular stack. So in this case, you can actually also implement any of these DFS traversals using recursion, and you're kind of like implicitly building a stack through all of the call frames. You don't have an explicit representation as a data structure, but either one of those would work. All right, cool. So this next question is going to be a binary search tree question. So again, The most important thing to know here is that a value, so if this is like a representation of a binary search tree, I'm just going to represent it with something like this. So if we have the value C at any node in our tree, the values to the left, so they must have values that are less than C, and the values to the right have to be greater than C. So this is a subtree with all values less than, and similarly, the right is a subtree that has all values greater than C. So this is basically like what the definition of a binary search tree is, and that's what is useful for this question. Basically, the problem here is that this doesn't actually like consider at any point like anything of more of a global picture. It's only looking at kind of like an individual local picture. So what it does is it checks basically, so if it's null, it returns true. That should be fine. Then it does two checks here. So this check and this check. These two are effectively just saying, is my left in violation or is my right in violation? So you're basically only looking at like this particular node here and its left and its right. You never actually have like this global picture that we kind of discussed over here, which is basically like everything to the left of a specific node must have a value less than whatever this is. Everything to the right must have a value larger than this. So an example that kind of exposes this, there's various examples that you could construct, but the one that I have, which is like a slightly smaller example, is just if the root was 3, to the left could be the value of 2, to the right could be the value of 4. So if we look at the two different perspectives here, so if we're looking at the first one, we would look at this picture here, which is 3 and 2. Is the value of the left less than the value of 3? Yes, it is. There's no value to the right, so it would return, it would not error out and say false there. We can then look at this triplet here, which again is missing a node. Is 2 greater than 4? Yes, 2 is greater than 4. That means that this entire thing, so it basically evaluate every single one of those and see that all of those are going to be, all of those will be true. And in that case, you'll end up with something that says, okay, this is true, even though in this case, we can see that because this value 4 is to the right, so it's to the right of 3, that means that there is a value left of 3, which is greater than 3, which does not work. To think about like why this is problematic, or like why you wouldn't want to have a structure like this, the whole idea in a binary search tree is that you can search for things efficiently. And how do you search for things efficiently? You kind of know where they are in the tree. You need to have some kind of structure. If you know that it's not to the left, you can basically say, I don't need to look at any part of the left tree. I'm only going to look at the right tree. And if you can apply that at kind of every single step, that can speed up your search algorithm a lot. And you could do a search, assuming that your tree is balanced, you could do your search in roughly log time. But if you have a tree that has no ordering, you have to look at the entire tree to find something, which means that would end up being a linear operation. And as we've discussed previously, like a log operation and a linear operation, like there's a huge discrepancy in time. If you have like 1 million items, that would take like 1 million steps for a linear function. And depending on what the base is, that could take like 6 steps for something that's log, if it was like log base 10. So it is like a very big difference. So basically, how do we fix this? We want to, again, kind of have more of a global picture. So what exactly, how exactly can we achieve that? So let me change the color. Why can I, there we go. Make this blue. Okay, so how exactly can we go about this? We're basically going to introduce a minimum value and a maximum value as our parameters here. Why are we doing this? We want to be able to keep track of a more global perspective of what's going on. And what we can do to instantiate that is just pass in, if it is not in this range, then that means that I have some kind of value. So if you can imagine what we first start off as is when we're calling this on the root, it can take on any value between the minimum value of integers and the maximum value of integers. So it's basically like the entire number line is up for grabs, and there's no problem if the root node falls anywhere in that range. As soon as we find a value, so in this case, whatever t.val is for the root, we then take that entire number line and we split it in half. Now, everything to the left can have values that fall between the integer min value and t.value. And then on the other side, all of the nodes should have values that fall in between t.value and integer.max value. So it's basically like we start off with this whole number line. We're then going to cut it in half by, or maybe not directly in half, but we're going to slice it into two pieces by whatever the root value is. Then we have two pieces. Then that piece, it has a corresponding like left child, and I need to slice it into two pieces. And each of those pieces has a corresponding range. If you see some value in that range that doesn't have some value in the tree that doesn't have a value that falls within that range, that basically means that you have some violation and you should have you should return false. So that's basically what we have here. So this code again passes in the min value and the max value as the starting two values. That gives us this corresponding start, which is you can use all of the possible values. So if t is less than the minimum or t is greater than the maximum, that means that it falls outside of the range. So we should return false. Otherwise, we should go ahead and keep recursing on both things. What should we recurse on? So we recurse on t.left. So again, we're taking the left part of the range. So it has to be everything that's less than t.val. So the now viable options are anything between whatever the minimum passed in is and t.val. And then for the right-hand side, again, we'll call it on right. Now we're going to split the range from t.val to whatever the maximum value is. So it's basically like at every single step, we're going to take this number line, we're going to slice it, slice it, slice it, and then we'll have two calls, and each of those two calls will have a different range passed in corresponding to how it's been split by t.val. So now we're going to talk about game trees. So a few things. So I'll just, again, kind of like very high level intuition of why we want to use this. So game trees are used to solve games or other kind of problems where you have a set of states and you're trying to figure out basically, I'm at a specific state and I want to decide how to move on to my next state. So what you can imagine here is like you're this player here and you're trying to figure out how do I go from whatever state that is here. I have two possible moves. So it's like there's move A or there's move B. And I want to know which one of those moves should I take to maximize my score. And exactly what that score is kind of up to you, but basically like you want to make your score as high as possible. And you can assume that you have an opponent that wants to make your score as low as possible. So in this case, we have these nodes. These are the maximizer nodes. And then these are the minimizers. So the maximizer, again, is trying to make the value as large as possible. The minimizer is trying to make it as small as possible. In this case, the whole idea here is that you want to pick either this move or this move based on this. So basically what happens is say you pick move A, that then is now the other player's turn who's trying to minimize, and that player has two options it can make. So it's like you have move A and B available, then say you take move A, then the minimizer has options like A or B available. And then say you take move A, then the minimizer takes move A, then you again have multiple options here. What exactly do these correspond to at the bottom? Typically, it doesn't make sense to carry this all the way to the end of the game. So the end of the game would be like, okay, you won or you lost. But typically you would have some kind of finite horizon. So in this case, that's like 3 moves here. And then you have these nodes down here, which are like static values. So these are kind of like the application specific part of a game tree of saying, okay, if I started at this position here, and then I took move A, minimizer took move B, and then I took move B here, that would result in a game that has this value 11. That value 11 is like very much relative, but basically what you can do is come up with some kind of static evaluation function. This is part of what you'll have to do for project 2 that says this state of the board or this state of the world is worth 11 points. And how exactly you define that is very much open to interpretation. It's a very domain specific thing. So there's specific things that, and if you've started project 2, that you might say, okay, like a specific configuration leads to a state of the board which I think should be worth more points. You'd have to encode that somehow and then return a value. What the min-max tree does is basically fans out all of those options, looks at all of the possibilities, looks at all of these static evaluations, then says, okay, the best option would be if I take move A. So how exactly does that look? So first we'll talk about 2 different things. So first we're going to talk about just min-max, and then we'll see what happens when we optimize it using alpha-beta pruning. So just using min-max, we'll basically look at the tree from top to bottom. The maximizers are always trying to find the maximal value, and the minimizers are always trying to find the minimal value. So if we start at this node right here, so this is a maximizer node. So this maximizer is maximizing over the possible values of 3 or 7. So again, it's a maximizer. It'll take the largest thing possible. The largest thing available is 7. So it would take 7, and that's the value of this node here. Similar here, we have a maximizer. This maximizer is maximizing over 10, 11, or 4. It's going to take the maximum value, which would be 11. Here, it's maximizing over 2 and 5. 5 is the maximum value, so the value of this node is 5. Last but not least, this is maximizing over 8 and 6. 8 is the biggest value, so we'll put 8 in this node here. At the next level, this is a minimizer. So the minimizer is doing the opposite. It's trying to find the smallest possible option to make your score as small as possible. In this case, 7 is the smaller score, so the value of this node is 7. Similarly, over here, it's trying to max or minimize over 5 and 8. Of these two, which is smaller, 5 is smaller. That's the smaller option. The minimizer chooses that. Last but not least, the maximizer at the very top is trying to maximize over these 2 values here. Which of those 2 is the largest? The largest is 7, so it'll choose the largest value of 7. So in this case, what we would see here is that the highest score obtainable, assuming optimal play, if you're playing against a suboptimal player, that kind of doesn't work. But assuming that you're playing against someone that is using the same kind of min-max strategy, you cannot get more than 7 points. And correspondingly, the best move that you can take is whatever this like move A is that corresponds to moving from this game state here into this game state here. So the way that they would actually work, there's various ways that you could implement it, but basically you would say, okay, I'm at this, and this is like maybe in the context of project 2. So I'm at this particular state of the board, and now it's asking like for the AI to decide what to do. So in this case, the AI says, I know from here, I can look at all of the possible moves available. So in this case, let's say there's only 2 possible moves available from this current state of the board. From this current state of the board, say there's only move A and only move B. You want to decide, should I take move A or should I take move B? In general, it'd be like, there's maybe like even hundreds of options. Which one of those would you take? So say you take move A, that corresponds to you've transitioned into a different game state, and now the side or the opponent has now taken their turn. So it's like you get to choose out of these options what are available, but down here, it's not your choice. It's whatever the minimal option is, and the minimizer will take care of that. So it's basically like I'm going to look at all of my possible moves here and try and figure them out. From here, I can see that these are all of the options here. I'm going to now say, okay, let's consider that first move. From here, what are all of the possible moves that the opponent can take? Say it's only these 2. From here, there's only 2 moves that can take. And then you'd finally say, okay, I'm going to not let this go for like some infinite amount of like moves into the future. You say cut it at 3, and you say, okay, if I take this move, they take this move, I take this move, how do I rate what state I get left in? And you're basically saying, okay, after any 3-move sequence, what are the possible scores that are available? And then you want to do whatever is optimal to get the highest score possible given that information. So you do start at the top, and then when you start at the top, you kind of fan out. But in terms of like if you were going to do it like on a test or on a worksheet, you can kind of work from top to bottom because that's kind of like how the values are propagated upward. This picture is a little bit misleading. You don't actually necessarily need to calculate all of these values. Like in this picture, it's like, okay, they're all there. I need to calculate all of them. The way that it would typically work is you would start at whatever the top node is. This also is like if you're using alpha beta pruning. So alpha beta pruning is basically like some way of cutting off parts of the tree. Because ideally, like we don't want to look at this entire tree. Because you can imagine like, maybe not for a game like this, but a game like say like, I don't know, chess or Go, where there's like dozens or hundreds of moves at every step. Then at every single level, like here now there's not 2, there's 100 options. At this level, there's not 2 options, there's 100 options. There's 100 options here. Then there's 100 options, 100 options. There's like this huge, like it like exponentially starts to expand. And if you had to compute like every single one of these, that would end up being like a massive amount of work. Alpha beta pruning is a way of looking at kind of like, as I start to see values, do I need to keep looking at this part of the tree? I'll explain a little bit more depth what that actually means, but basically you can use it to say, okay, there's nothing in this part of the tree that would ever result in something that is a better score for me. So I shouldn't look at it. I shouldn't waste the time like going through all of this part of the tree, then calculating all of these values here, because that does take a lot of time. As soon as you find out that like this branch or some part of this subtree isn't going to result in something better, you cut it off and then move on to something that could give you a better score. So in practice, like what you would be doing is you wouldn't be calculating all of these. You wouldn't calculate them at first. You would kind of, as you go through the tree, make decisions of like what parts of the tree that you don't need to look at that you're going to cut off. For all the other parts, you will need to calculate these values. So alpha beta pruning is, I typically like to think about it not using the values of alpha and beta because I think it makes it a little bit more straightforward to explain. The best thing to do is like, and this is probably not like a very helpful thing to do, but just think about like options like when can I actually get a better result? That's kind of what alpha beta pruning is. So alpha beta pruning is basically saying, if I cannot get a better result from this part of the subtree, do not consider it and just cut it off. So if we start off at 7, so imagine that we don't have these values calculated yet. So I'm gonna go ahead and erase these values for just the sake of going through this again. So I'm gonna start off at this node here. If I'm starting off with this node here, I have absolutely no information about what any of the point values are. So I have to go down and we'll just say we're gonna visit the left first. So now I go here, again, I have absolutely no information here. So I'm just gonna go down into the left again. Finally, I get to this point here. Again, there's no information here, but I know I'm maximizing over 3, and I know I'm maximizing over 7. So these are the two things that are being maximized over, and we again said before this was value 7. So if I see this 3, do I need to look at this value 7? So in this case, we do need to look at this value 7, because if I see a 3, it's possible that the next value I see here could actually increase the value of this node here. So I see the 3, I say, okay, I need to keep looking through the other children of this node here. In this case, I see 7, and that says, okay, now I found a better value here. So I'd fill in this value 7. So for the first kind of little subtree here, you have to look at all of these values to get some concrete value. You now return up to this minimizer. So from this minimizer's perspective, you basically say, I see there's some way for me to get 7 points. And there's whatever this arbitrary like other option over here is. So I will only pick something that is 7 points or fewer than 7 points. So if I am the minimizer and I go to the right, I have to say how many points is this worth? I then say, okay, so I basically started here. I'm trying to figure out, should I take like this 7 or whatever this option is here? I then go down to here. I see this first option. This first option is a 10. So if I see a 10, from the minimizer's point of view, what do I know? I have already found some option that is going to give me 0.7. The minimizer knows that this node here, this will take something, whatever it is, that's larger, the largest value that it sees. If I see this 10, that means that the value of this node is either 10 or it's more than 10. So what does that mean? That means that I shouldn't continue to look at these two nodes here because it will only be a value that's larger than 10. So if I look at this value of 11, or I look at this value of 4, that's only going to make this number something that is already larger than 7. So that means that the minimizer should say, I don't care about what this number is. I don't care about what this number is. I already know that this node is going to result in a value that's higher than this node, so I will already pick this node here. In that case, you can prune off this, these two parts of the tree. So does that kind of make sense? So it's basically like, I have found something that I know will be bigger than this, and I'm the minimizer. So I'm always going to pick something smaller. So I see something larger, and I just say, okay, I'm going to stop this entire part of the tree. I know I won't take it because I found something better over here. So let me just discard this. And then what do I know here? I know that I'll take the smallest thing here. So in this case, I'm just going to take the value that I already know, I've already computed, and say that it's 7. So now we're looking at the maximizer. So the maximizer, again, has basically seen, okay, I know I can get this value of 7 somehow. And basically what the alpha and beta values are, so I'm not really talking about what they are, but it's basically like this way of keeping track of, oh, I've already seen something that's this big, or I've already seen something that's this small, and basically kind of maintains that whole like, when do I decide to stop? So this maximizer knows that it can see the value of 7. It's never going to take something that's less than 7. So I go to the right here. I don't know what the value of this is. So again, I'm going to go down to the left. I go here. I don't know what the value of this is. So I'm going to go here. So I see this node, and I see that it's a 2. What does that mean for me? That means that this value of the right tree, this is at least 2, because I know I can get 2 here. Should I go ahead and look at this node here? In this case, another way to think about this is like, what if this was a different value? Could it cause me to have a better score? So in this case, we see that it's a 5, and that doesn't actually give us anything better than a 7, but it's possible, what if this was instead of 15? And then this node could be a 15, and then it's possible that this could be something that's even higher, and then this minimizer would have to take this node, and then that could actually cause my value at the top here to change. So it's basically like, you can kind of consider these like hypotheticals, like, what if this was a larger value? Would that affect what the value actually is here? Again, we're only cutting off parts of the tree that will not affect what the value is. So in this case, we do need to look at this. So we look at the 2, we look at the 5, and we say, okay, the maximum value there is a 5. So now we're back up at the minimizer, and what do we see at the minimizer's level? So we were like kind of optimistic, okay, like maybe we could get something that's better than 7, but at the minimizer's level, what do we see? We see, I know that this minimizer is either gonna pick this 5 or something that's less than a 5. So do I need to look at any of this part of the subtree over here? In this case, no, because I know that the minimizer is gonna pick something that is 5 or smaller, so there's no way this could be something better than 7. So in this case, you can prune this entire section of the tree here, which would effectively be like pruning these branches off here too. In that case, what do we see? We know that the value of this node here should be 5 or less. So I'll just write like 5 minus. So it's something that is 5 or something that's less than 5. In this case, we know that at the very top, this maximizer is going to take the maximum thing. So it's choosing between something that's value 7 or something that has a value of 5 or less. So what should it take? It should take option A, which would be, okay, I'm going to get 7. So again, what we see here is this doesn't actually change the end result. The only end result that we really care about is at the very top, which is basically like, what is the value of this, and kind of like what move would we take from here? It depends on exactly what you're coding. So sometimes this is like a very like domain specific thing. So there's like maybe not a very general implementation of this data structure that allows you to pass in anything. It's also possible that you could specify some kind of like interface. It's like, I can run a game tree on anything that has like this like next state function and anything that has basically the static evaluation function. And then it's like, okay, you could maybe generalize it like that, but this is like a very specific, so the overall structure of how you work through the game tree, that itself would maintain the same thing from like one problem to the next, but the static evaluation function is like it has to be defined for that particular type of game, that type of problem. So it's like, if it was say like blackjack, there has to be a specific way of saying, okay, like a simple, or maybe like a simpler game would be like tic-tac-toe. So tic-tac-toe, it's like advantageous if there's an open spot for you to win, or it's like advantageous if you, like certain moves might be advantageous or not, and you can score that in some way and specify that. If you're considering a different game, like Connect 4 or something like that, has its totally own different model of what looks good. There might be some shared similarities, but it's like for every specific application, there must be this whatever static evaluation function, and that must tell you how to evaluate this board. You would basically say, considering all of these different steps that can lead me to a different spot, what does that result me in? That results me in a specific game state. And then you say, with this specific game state, what is the static evaluation of that specific game state? And then from there, you can propagate the values back up.